Thanks everybody for joining us, and thanks to Genevieve for setting this up. And not for the last time, thanks to the South Central Climate Science Center for supporting this research. We're here to talk about predictions of water supply in the Rio Grande Headwaters, and I want to make it clear right up front that I'm a climate guy mostly, so we'll be talking about climate style forecasts on two time scales, seasonal time scales. Those are the so-called water supply outlooks that lots of water managers use very heavily, based largely on snowpack from the headwaters region. So from a climate perspective, really what we're looking at is what happens to water supply, that is the seasonal average water flowing down the river during a time when the temperature is rising and the snowpack is diminishing. And we'll take a look at two different timescales. One is the seasonal prediction timescale, and the other is a long-term climate change projection timescale. And so what we'll try to use the two timescales to inform the other, and we're going to come to basically the same kind of conclusion about what processes are important to understand in order to help us make predictions or projections on these timescales. I want to very quickly acknowledge Shailene Chavarria and Nels Bjarki, two grad students who actually did all the work. I'm just talking about it. Shailene now works for USGS here in Albuquerque. Nels is in the PhD program up doing hydrology up at the University of Colorado, and they did great work on this project. You'll see their names over and over again in references as we go along. And then let's just make it real clear where this talk is focusing. So there's a map on the left here of the very long Rio Grande system, and we're just talking about the very northernmost headwaters region up in southern Colorado. A very large fraction of the natural runoff into the Rio Grande comes from this region at the far northern edge of New Mexico and southern Colorado. And we have done an extensive analysis of a stream gauge, which the Coloradans charmingly call Del Norte, which is located right where the headwaters leave the mountain front and reach the San Luis Valley. Del Norte is a place where, I won't go into this in detail, but where we have demonstrated that the natural flow coming out of the mountains is relatively unimpaired. And so the gauged flow at Del Norte and its variability, we think, is a good measure of natural processes, climatic processes happening up in the headwaters region. Okay, so here is the basis for an awful lot of seasonal forecasting. So what we're looking at here on the left, those black lines are this is an old plot, but this is the seasonally averaged over many years, the snow water equivalent starting at the beginning of the water year on October 1st. We have a snow accumulation season that extends into early April. And then on average, we have a fairly rapid decline in snowpack as the snow melts. I have to say, as an aside, I'm cheating here. This is a plot I like because I like the way Carrie Jones did it. It's actually from just over the divide at the headwaters of the San Juan River, but this snow seasonal cycle would apply perfectly well on the other side in the headwaters of the Rio Grande. So this sort of snow seasonal cycle um, translates at the Del Norte gauge into an average hydrograph that looks like this over here on the right, such that we have a low flow season in the winter, with the flow ramping up rapidly in April, reaching a historical snowmelt runoff peak in June. That's during this snow ablation season as the snow melts. And so, you know, we can just eyeball here that an awful lot of this runoff season peak, and therefore an awful lot of the overall flow in the river, is coming from melted snow. But we can say more than that, because these two plots here show on the left all the years in a data record where the snow was below average on the kind of historical peak snow date of 1 April. So we often use 1 April as a standard date for near peak snow. And these little faint lines here are all the years in this data record where the snow ended up being below average on 1st April. And over here on the right, we've the average is the same, and now here are all the years in which the snow was above average on 1st April. And so what you can see is that we actually get some cheap and easy predictability from snowpack in this record, because if it's true that lots of the snowmelt runoff is coming from this snowpack, and we can relate, as we'll show you, variations in runoff from year to year, in variations in snowpack on 1st April, we can predict whether we're going to have above average or below average snowmelt just by taking a measurement of snowpack on 1st April. And not only that, we can look backward in time, because almost all the years where the snow ends up being above average on 1st April are years in which the snowpack was above average on almost all the dates in the early part of the year. So we can make a prediction with some skill, considerable skill, in January or February or March about whether we're going to have above or below average runoff based on just measuring the snow. And the same is true for the below average years. So predicting water supply historically has largely been a matter of measuring the snow in the headwaters at a few point measurements, now SNOWTEL, formerly snow course measurements, and translating that using some statistical regression scheme into above or below average runoff season discharge down at Del Norte. However, this is getting harder. And the reason it's getting harder is first illustrated if we look at how this hydrograph has been changing. This is for a relatively old set of years, going back into the 50s, into the mid 80s. And then this is actually the first half of the data record that we used at Del Norte. And if we ask, how has the flow been changing from the first half of the data record to the second half, we get this result here, in which we see that flows have been decreasing in the latter half of the runoff, the discharge season. And if anything, they've been increasing a bit in the first half of the discharge season. And that's because the snow's been melting. So we're getting somewhat less snow, and the snow that falls melts earlier. And our task today is to ask how all of that is going to change the predictability of snowmelt runoff in this system. So here's some time series. There's a somewhat more detailed map of the headwaters of the Rio Grande there on the left. And so what Shailene Chavarria did, that was subsequently updated by Nels Bjarke, was to take these snow course sites in the Colorado Basin, not all of which actually are upstream of Del Norte, but we took an average of all those sites. And Shailene did some variance weighting via an eigenvector analysis. but came up with this time series that goes back into the 1950s. So if we want to go that far back in time, we have to use the older snow course measurements, not the snow tell measurements. But we've analyzed the more recent data just to show that, at least for now, the snow tell and the snow course measurements track each other pretty well. When we do that and try to come up with a basin average snow estimate for 1st April every year, we get this green curve, and the green curve has lots and lots of ups and downs. Which I'll just tell you for now are related to snowpack and precipitation generally. But superimposed on that is a downward trend shown with the dashed green line. And if you actually read off the numbers, that's a pretty alarming trend, because it shows that since the mid to late 1950s, there's been an average decrease just measured by that trend line of 25% in snowpack. So the snowpack that is feeding this river is melting. And this is not brand new news. Lots of folks, such as Phil Mote, have shown that this is true across the West. Temperature is rising, snow is melting, snowpack is going away. During this time, however, we have only a minimal decrease in terms of the trend in the stream flow measured at Del Norte. In this case, an annual stream flow. So one of the little conundrums we'd like to address is what could cause a rather dramatic decline in snowpack together with a relatively minimal decrease in stream flow. Okay, well, why is the snow melting? And here's why. It's getting warmer, and it's getting more. These are glorious English units. 3 degrees Fahrenheit increase in the headwaters in recent decades. That's an annual measure of temperature, but we would see the same results if we looked in say, the snow ablation season. So we are experiencing rapid temperature increase that's entirely consistent with increasing greenhouse gases and the model simulations that are simulating global climate change. During this period of time, there's basically been no increase or decrease in annual precipitation. So we have a system that's warming rapidly, but where the annual precipitation is not changing much. And if we look at how the precipitation has been changing by month, what we see is maybe makes things a little bit more alarming, which is that this zero decrease in precipitation has amounted to an actual increase in the winter and spring months during this time, from the first half of the record to the second half of the record, which suggests that the snowpack decrease we just looked at in recent decades has happened in spite of, if anything, a weak decadal increase in the total winter precipitation. So the ratio of snow to total precip is plummeting as the temperature rises, and we see a relatively modest overall change in precip, but lots of interannual and decadal variability. Okay, so here in one slide is a summary of what we've done with these data to try to figure out what is happening to seasonal predictability of snowmelt runoff at Del Norte. And the punchline, one of the punchlines is that we're just losing predictability based on snowpack in order to make estimates of the snowmelt runoff coming after the snow melts. And the way we've done that is just to look at the correlation between different climate variables, snow and on April 1st, and temperature and precipitation in the spring season after peak snow, so April, May, and June. And those results are summarized here on this bar graph. So this bar that's got little snowflakes in it is the R squared value, it's just the square of the correlation between interannual fluctuations of runoff season stream flow and 1st April snowpack. And what we see is that for the 30 years back in the 50s and into 1980, this R squared value was up around 0.8. In other words, you could capture 80% of the interannual variance of runoff season stream flow just by looking at 1st April snowpack, which is a winning way to make a prediction. It worked great. If you knew how much snow was up there on April 1st, you could make a hell of a good stream snowmelt runoff forecast, which is the water supply outlook. And what has happened as the temperature shown by this red line has gone up is that this snowpack bar has just gone down. So that in the most recent 30 years, when this analysis was carried out now, we're now a couple years ago, this R squared value was down to less than half. So the simplest way to make a snowpack-based estimate of stream flow is going away as the snow has melted. And so we ask what has happened to that variance. So these pie charts here show the same kind of numbers. The snowy wedge of the pie is the variance accounted for of stream flow accounted for by snowpack in the early decades, basically the first half of this record. Every black wedge is a residual, that's unaccounted for variability of stream flow. And then these two other wedges represent spring precipitation and temperature. The punchline here is that as the snowpack snowpack related variance has decreased in this regression exercise, two pie wedges have increased. One is just the residual. So we make less skillful forecasts in this regression-based procedure, which is pretty close to the way the NRCS goes about making its operational water supply forecasts. The residual is getting bigger, which means that our overall prediction skill is decreasing. But what is accounting for an increasing amount of variance as the decades roll on, the temperature rises and the snow melts, is spring precipitation. So spring precipitation is now accounting for an awful lot more variability of snowmelt runoff and as a compensating or accounting for more of the variance not that we can't account for using snowpack. Temperature is playing very little role here. We're not getting an awful lot of predictive information from springtime temperature. And that's a result that's at odds with some other studies that have emphasized the increasing role of temperature as a predictor of snowmelt runoff. In our analysis set up this way, the information contained in the temperature trend is basically embedded in the snowpack. So from this analysis, we conclude that for improving seasonal water supply outlooks, the variables that matter are snowpack is still important. That's still our most important predictor, but increasingly spring season precipitation is the variable that we think we need to understand in order to make better seasonal water supply outlooks. Okay, let me switch over and summarize what we've done with this kind of information and applied it to longer term projections of future stream flow change using climate models. So here, people have been making climate model projections of snowmelt runoff in western rivers and projecting lower flows for many years. And what I want to emphasize is that the variability from one projection to another is enormous. But there is a consensus that what we ought to expect as the snow melts in a warming climate is diminished flow in pretty much all southwestern rivers. Here's the Rio Grande in an old projection carried out by Milley et al. Brian Hurd and Julie Coonrod published a paper for the Rio Grande itself showing a shift in the average hydrograph toward less snowmelt runoff melting earlier, which is actually what we're starting to see. So in addition to projecting less flow late in the snowmelt runoff season and perhaps more flow early on, as we move out later into the century and the snow melts, we should expect, according to their projections, less snowmelt runoff at all. We're going to use some more recent projections disseminated and generated by the Bureau of Reclamation. So they've taken so-called CMIP-5 climate model simulations, an awful lot of them, 97 of them that we've worked with, and published the results of coupling climate model results to a hydrologic model, VIC. We can talk about this later if there are questions about that. In order to couple the coarse resolution climate model results to the hydrologic model, they need to statistically downscale the climate model results. They've bias corrected them to make natural flow simulations. And here is an envelope of all 97 simulations showing a very modest downward trend, which is consistent with what most everyone else has projected, but with enormous variability from one projection to another. And so we would like to ask if we can narrow the uncertainty within this envelope of uncertainty by taking the results that we've obtained from the observations that I just discussed and applying them to see which of the models that go into this ensemble average can reproduce the trends we've seen in snowmelt runoff relationships in the historical period. Let me add as an aside that we have found out kind of the hard way from both giving talks at meetings and from journal editors that there's a lot to pick at in these simulations if you choose to. Some people don't like the downscaling, some people don't like the bias correction. Nevertheless, this is, I think this is an important set of simulations, part of Reclamation's West-wide climate risk assessment. And I think we are gleaning some valuable information from them, as we'll see. Okay, so what we have done is tried to identify what I'll call observationally consistent simulations out of this ensemble, using simulations carried out over the historical period, which is the same period of time we've analyzed observations. And so we ask which of these 97 simulations successfully reproduce at some level a very high correlation between snowpack and runoff in early decades that decreases in later decades in the historical period as temperatures warm up. We look for simulations that exhibit some decreasing predictability of runoff as the decades roll on in the historical period. And we are looking for simulations in which the variance of stream flow accounted for by spring precipitation goes up. And what we find when we ask models to reproduce that set of criterion is that only 14 out of 97 simulations meet all four criteria, passing an admittedly fairly arbitrary quantitative threshold for meeting all of these metrics. And furthermore, we find that the simulations are not consistently observationally consistent or not within model ensembles. In other words, the same climate model is run multiple times in this group of simulations using different future projections for greenhouse gas concentrations. which should not affect their ability to simulate the historical period. Nevertheless, in some of those groups, one or two model simulations might be observationally consistent and the others are not. And our conclusion from that is that the assumption we're making here, asking these models to reproduce these results, there's an implicit assumption here that these signals are forced climate changes, that it's not just natural variability, it's not just cyclic that we ought to see go up and down, that we're asking models to reproduce this as a forced climate change. And that is probably not 100% true, that there's a huge amount of natural variability, both in the observations and in the models. And so the moral of this is that we ought to be a little bit humble in what we ask models to reproduce. Another obvious challenge here is that we're asking models to reproduce these signals in what by climate model standards is a small watershed, a pretty small area. And so it doesn't take a huge shift one way or another of storm tracks or something in order to not get the right answer. Nevertheless, we will think about what we get out of these 14 simulations out of the 97 that are observationally consistent. And here's what we get in a nutshell. I'll turn to this plot in a moment, but we've just looked at the average change from the late 20th century simulated to the late 21st century simulated in the change in stream flow at Del Norte and the change in first April snow. And here is the distribution from the observationally consistent simulations, and here is the distribution from those that are not observationally consistent. And that's seen here on this plot. These yellow dots are observationally consistent simulations and the dinky dots are not. And so when we focus our attention on the models that are observationally consistent, we reduce some of the spread in the models, and we get, by and large, simulations that project significant declines in snowmelt runoff. So we think by doing this, by picking winners, as it were, among the model simulations, we increase our confidence in the simulations that are predicting less runoff along the y-axis on this line, because those are preponderantly the observationally consistent simulations. Lots of these other simulations that are projecting actually big increases in stream flow and spring precipitation are not successfully reproducing the trends we've seen during the historical period. And so we would assert that we have less confidence in them. So we think we've reduced the uncertainty to some extent among these simulations. The other thing I'll emphasize here is that we've plotted the change in stream flow for all the simulations on the y-axis against the change in spring precipitation simulated by the models. And what we see is that all the simulations, but especially the observationally consistent simulations, scale their projected change in stream flow by the projected change in spring precipitation. So much as we concluded in our assessment of the seasonal predictions, in terms of these long-range projections, we also claim that spring precipitation is probably a variable of tremendous interest in trying to narrow these uncertainties further. So consistent with our assessment of interannual variability in observations, using climate models and looking over much longer timescales, we find that the two variables that count for the most in modulating snowmelt runoff are snowpack and its changes, and spring precipitation during the snow ablation season and its changes. And so there's some consistency here between the OBS and the models in terms of the variables that really matter. Okay, so just to summarize here, we've confirmed that the climate is changing in ways that affect water resources in snow-fed rivers. Temperatures going up, snowpacks going down, that's what we've seen in the past, and that's what we expect to continue to see into the future. We haven't seen definitive long-term trends yet in precipitation or stream flow, and in large part, we think that changes in precipitation that may be natural on decadal timescales have modulated in this system the effect of declining snowpack directly in diminished runoff. But what we have seen for sure is that this trend toward diminished snowpack has decreased the seasonal prediction skill that we would get just by observing peak snow. And as snowpack becomes a less important predictor, then spring precipitation in the snow ablation season is becoming more important. And here are the two most important variables that we think we should focus our attention on to improve matters and to better simulate and predict snowmelt runoff. Snowpack and spring precipitation are the variables that our analysis identifies. Then when we look at long-term projections, we see also that in models, temperature going up, snowpack going down. I'll show you in a minute that there is an overall assessment of diminished spring precip, but that's certainly what we saw in the observationally consistent simulations is a decrease in spring precipitation together with a decrease in snowpack. All of these long-term projection conclusions have to be tempered with the understanding that natural variability in this system is really large, and so it can be very difficult to tease apart decadal scale fluctuations in precipitation and runoff with long-term trends. Only a few of the streamflow projections we derived that we looked at are observationally consistent using the rather stringent criteria we set up. But the simulations that are consistent with what we've seen in the historical record tend to confirm that we should expect lower snowmelt runoff in the Rio Grande Headwaters. Okay, that's only slide 11, and my counter says I have 4 slides to go. So what I'd like to do is conclude with making a few editorial comments on where we might take this kind of analysis into the future. Remember our 2 principal climate variables of interest here are snowpack and stream flow. So one thing we'll want to do moving forward is improve our estimates of observed snowpack. And here I assume I'm preaching to the choir. I know the CASC and USGS in general are already supporting efforts to try to make quantitative estimates of volumetric snowpack. And that's the wave of the future, that these point estimates illustrated here from maps from earlier this spring are what we've used historically, but I think it's a really exciting time when we can look forward to improved estimates of snowpack that aren't constrained by just a few point measurements that are going to be harder to use as the snow data become non-stationary, as the snowpack retreats up the slopes in warmer temperatures. But I also think we ought to pay more attention to long-term estimates of snowpack and as a way to understand what's going to happen to water resources in the West. These plots are from the latest National Climate Assessment. We haven't done an awful lot historically with climate model projections of snowpack. We've paid much more attention to projections of temperature, but I think we're, as we move forward and regional downscaled models, efforts such as Cordex will make a more detailed assessment of snowpack projections and analyzing those much more explicitly and in detail is where we will need to go moving forward to relate climate model projections to water resource changes in the future. Then the other variable that matters for our story about snowmelt runoff is spring precipitation. And so here are some examples of seasonal forecasts put out operationally by the Climate Prediction Center. And I would like to make a pitch based on our results in part that it's time for us to start integrating seasonal climate forecasts of temperature and precipitation explicitly into our water supply outlooks. The NRCS has shied away from this historically, not thinking that there was enough prediction skill in the climate forecast to make a difference. And I think we should reassess that judgment at this point. And I think it would be worth our efforts to try to come up with an integrated seasonal forecast system that includes deterministic climate forecasts of temperature and precipitation, and actually using them to improve our seasonal predictions of water supply and stream flow. And then on the long time scale, here is the map that I think we're going to be paying attention to a lot for the Rio Grande, and I suspect for other river systems as well in the West. And that's the snow ablation precipitation outlook over the long time scale. This is for the late century, projected change in spring precipitation, again from the latest National Climate Assessment. And it shows projections of diminished spring precipitation here in the Southwest. It gets a little bit dicier. This hatching means less confidence as we move farther north into the headwaters of, say, the Colorado River. But this is an outlook that we will want to improve our confidence in if we want to improve confidence in the water resource outlooks on long time scales that a lot of people are really interested in. Okay, with that, I will thank you all for listening to this quick summary of what we've been up to on the Rio Grande system for the last few years, and express my sincere thanks once again to the USGS and the CASC for supporting this research.